In this lecture, I will be talking about neural networks. The lecture consists of 3 parts. In the first part, I will give you basic principles of neural networks and will discuss how we compute the gradient needed for parameter optimization. In the second part, the principles of optimization itself will be discussed. The third part then consists of practical issues for working with neural networks. You may have seen this before. Suppose you have a number of data points from a certain process. Here the data points are the blue circles, while the process itself is described by the green line. We call our inputs x and our targets z. Z is subject to measurement noise. In most cases we assume this noise to be Gaussian. How can we model these data? A typical way and a very efficient way of modeling is by using linear regression. In this picture you see modeling with linear regression using a 0th order polynomial. Of course it's not optimal, but it's a very simple system. Finding the parameters of this model, in this case just the W0, can quite straightforwardly be computed by, for instance, using singular value decomposition, SVD. Of course we need to make our model more complex. Staying with linear regression, we add a second parameter W1 and a higher order to our polynomial. Note that the computational complexity is still comparable. You can still directly compute optimal parameters, now W0 and W1, using SVD. And so on. We can add more and more parameters, and again, with linear regression, solve this parameter search problem. You can actually see that this is quite a good solution already. We can continue adding more and more parameters to the system, making it more and more complex, in the hope that the results will get better and better. But this may not always be the case. The effect of overfitting you see here, note that in this picture we have as many data points as we have parameters, is quite serious. The general case of linear regression, as you have seen it in an earlier lecture, has a number of basis functions phi of x, and each of these basis functions is multiplied by its own parameter w. Even though this approach can be used to represent nonlinear functions, the parameterization itself is linear. It is therefore straightforward to find optimal parameters w, and indeed the associated optimization problem is convex. Only one optimum exists. That is why it is called linear regression. The regression is linear, but the result need not be. Typical basis functions that are used in linear regression are polynomials, or Gaussians, or sigmoids. Remember that Gaussians are given by this equation, and that sigmoids are typically given by this one. Or also by this one. Note that the mu's, they differ for each of the basis functions that are depicted in these figures. So the mu is actually a parameter of the basis function that must be determined beforehand. How can we find optimal basis functions? After all, often these basis functions have parameters themselves, which we have to somehow determine. Of course, looking at the data may be a good option, though one can also add incorrect interpretations based on some engineering assumptions. Anyway, all of this is not an option if the data is high-dimensional or otherwise complex. Now look at the schematic representation of the linear model we have discussed above. Our input x, which can be a vector of course, is fed through our nonlinear basis function. Again, note that these basis functions have parameters by themselves. Then the output of the basis function is multiplied by a parameter w and then summed up at the output. You can see this model as a very simple neural network. And now we have the components to extend this system to let it find the best basis function parameters itself. The representation we end up with is the following. Our input x is multiplied by a parameter and propagated to a unit, to which an additional parameter is added. This added value here is represented as a parameter from an input with constant value 1. From there on, we continue as before. But note that we no longer have linear regression. We have additional parameters within our phi, which need to be determined. Finding these parameters is no longer a linear optimization problem. This model is a neural network, sometimes called feed-forward neural network. It is also known as multi-layer perceptron, or MLP. Once we have this basic structure, we can go on adding more and more hidden layers. It is just a matter of making the neural network deeper and deeper, and thus adding more and more nonlinear basis functions and of course their parameters. In this picture you see 2 layers of hidden units, and currently networks of up to 6 layers of hidden units are being used. Note that in this picture I left out the connection from the constant input, also known as the bias input, but of course it should be there. How do we find optimal parameters W for our neural network? Well, we can still formulate the optimization problem just as with linear regression. For instance, assuming Gaussian noise in our data, we can express the log likelihood as shown here. In this interpretation, maximizing the likelihood means minimizing the sum of squared errors, which we call our loss or our error. But as mentioned before, finding optimal parameters W is no longer a linear optimization problem. E is no longer a convex function. It now has many minima, saddle points and so on, and finding an optimal set of W is now actually a piece of art. We need to revert to an incremental procedure for optimizing our parameters W. So we must minimize this error. Noted in our notation here, z is a scalar, but in the general case this can also be a vector. Now a minima of some function e of w means that the gradient of e at that point is 0. We need to find those points where the gradient is 0. How can this be done? Well, the most straightforward approach follows the negative gradient of e so as to minimize it. Oh, by the way, note we use notation nabla of e to indicate the gradient vector. How can this nabla of e be computed? Well, that is what backpropagation does for you. I am not going to do the derivation of backpropagation here. You may find very many online resources for this, and indeed it is not difficult to derive these equations. But the mathematical notation is always a bit messy and you need to get it right for an implementation. The general idea of backpropagation, however, is this. Suppose you have an error, and I call that residual, at the output. This error is simply given by y minus z. You can use this error to compute the gradients of the weights leading into that neuron. For the weights to the lower layers, you first have to propagate the output error back to the neurons below it. And you do this by multiplying the error or the residual at the output with the weight leading into it to contribute to the residual in the neuron below it. So the general backpropagation algorithm, which you use to compute the gradient of your error function, can be summarized like this. You start with the training sample, compute the output in the forward pass, calculate this residual at the output, and then propagate it back to the layer below that. The weight adaptation, and you can find that by solving your backpropagation and doing the math yourself, is then computed by multiplying this delta with the input x and with the derivative of the activation function at that unit. In the next lecture, we will show you how optimization in neural networks is being done and how we can use this gradient to compute optimal weights.